Now let's move on to section 3 of this notebook, area of surface of revolution. Here's an example. We begin with a parametric curve, a solid blue curve segment as you see in this picture, and rotate it with respect to an appropriate axis of rotation. Consequently, we're going to end up with this kind of picture. Kind of looks like a vase. And it's a surface, so the inside is hollow. This is a little bit different from solid of revolution that we dealt with early on. Oh, by the way, if you look at from this angle, you can clearly see that this is coming from rotation. Okay, those are some of the examples of surface of revolution, and we'll have to talk about surface area formula. Again, we're going to follow the same strategy as we did in section 2 of this notebook. Instead of going through all the rigorous details of derivation of the formula, let's just take this formula as granted and just apply this formula to a couple of problems, get used to those, and then let's move on to the derivation of the formula following through this natural flow of logic starting from the very foundation. The latter part is important, yes, but a lot of students may not be able to follow those very well. Consequently, I'm making a kind of compromise again. Oh, by the way, one more thing. In order to apply the surface area formula, you gotta know what this means here. Let's see. The integral part is pretty clear. T is running from starting time A to ending time B. And then the right hand side, this is our old friend, the arc length element, ds. The square root of x prime squared plus y prime squared dt, which is abbreviated by ds, is the arc length element that we already dealt with. So we know how to deal with it, and we know how to simplify those whenever necessary. And finally, this 2 pi r part, okay, finally I succeeded highlighting it. 2 pi r part. 2 pi, of course, or 2 pi part is not much of a big deal. That's constant. And also, it's not surprising pi shows up because this is surface of revolution. How about this r? R is the radius of rotation. Let's go back to the previous example here, and let's animate this according to the moving particle model. Then you can see the radius of rotation, which is represented as red dotted line segment from the particle to the axis of rotation, like this. In general, finding out this r of t may not be an easy job. However, in some cases, it may be much easier. For example, if you just tilt this picture and change the viewpoint, and you can make this curve into something like this. Let's make it a little bit bigger. Something like this. And what did you get? The axis of rotation, after a little bit of tilting, became a horizontal line, so you can regard it as an x-axis. Consequently, the radius of rotation is nothing more than the y-coordinate of this parametric curve. And of course, if you tilt it the other way around and then make this axis of rotation vertical, then the radius of rotation will become the x-axis. Kind of like these here. So when the axis of revolution is x-axis, then radius is y, and the axis of revolution is y-axis, then the radius is x. And of course, you can add or subtract some numbers when we have axis of rotation as vertical or horizontal line segments. If it is tilted in general, that's going to be a little bit more difficult. Okay, let's move on to an example. Let's move on to the simplest example, example A. Y equals 1/4 x squared minus 1/2 log of x. Now this is a graph of a function, isn't it? In that case, the typical technique is to take x equal to t. Consequently, the dx dt part is just 1. X and t are the same, so dx dx or dt dt, that's just 1. So we have just 1 squared. And how about this dy dt part? That's the same as dx dy dx, so that's going to be just a derivative. Kind of like this over here. Radius, r of t, is nothing more than the y-coordinate values, so we just use 1/4 x squared minus 1/2 log of x, and of course x and t are the same, so whether you use t or x doesn't really matter. Dx dt is 1, so 1 squared is 1, no big deal there. And now dy dt, that's the same as dy dx, so all you have to take is the derivative of the original function. That's right over here. 1/4 x squared becomes 1/2 of x, and then 1/2 times log of x is 1/2x. Now how do I simplify the square root part? The typical technique is somehow you have to get a complete square, but in order to get a complete square, it looks like you have to break up one's complete square. So let's break it up. A squared minus 2ab plus b squared. So a squared, x squared over 4, that's fine. B squared, 1/4x squared, that's fine. But middle part is interesting. 2ab, 2 times first term times the second term. Do you see cancellation here? Well, I see this 2 in numerator and then 2 in denominator canceling out, and also the x in numerator and x in denominator canceling out. Consequently, we have something like this. Do you have any further cancellation now? This negative 1/2, which was generated by this cancellation from the middle part, and then the first term, we have just plus 1/2. Now, please note that this is a complete square, because a squared minus 2ab plus b squared is now changed to a squared plus 2ab plus b squared. One more. We have this complete square and square root. After cancellation, we have something like that. Now, in order to be precise, we have to have this absolute value sign because we need positive, but in reality, you don't have to worry about it because this integral from 1 to 2, in this interval, this quantity is always positive. So I don't have to worry about the absolute value sign. So instead of that square root, I can replace that square root by 1/2 of x plus 1/2x. Now, computation is relatively straightforward. We have multiplication inside that integral, so break up everything and then FOIL. We have, well, bunch of addition. First function is a power function. That's easy to calculate. Next, we have another power function. Again, antiderivative computation is easy. Third, power function times logarithmic function. That's going to be an integration by part. Do you remember? Logarithmic function has the strongest tendency to become u. Consequently, this power function part will become v prime. And then apply the integration by part formula, and then you're going to get an answer. The final term is going to be an integration by substitution. If you take u equals to log of x, then du will be 1/x dx. The derivative of log of x is 1/x. So this x in denominator will be absorbed by this du computation, and you're going to get appropriate antiderivative as a u expression. So this example combines an exercise on integration by part and integration by substitution. Now, I don't want to finish that computation because that's tedious, and integration by part and integration by substitution are something you're supposed to be able to handle. So let's just go directly toward the rest of the computations. Here it is. And after calculating all the antiderivative, you get something like that, and then applying the fundamental theorem, plug in the top, plug in the bottom, subtract one from the other, we get this quantity. This is the precise value, and great. However, I don't know how large this is, to tell the truth. Log of 2, that's irrational, and pi, that's irrational. How large is it? Well, if you punch into calculator or ask Mathematica to do that, then here is the answer, 2.74 something, and that is the approximate answer, and that's also good. But in order to have an approximate, the digit string as an answer, you have to have precise answer along with it. By the way, did I do everything right? You can check everything using this Mathematica program, and this simplify command allows you to calculate the 1 plus y prime squared part, and here it is. And please note that that's square, so you can always take the square root of that, and then you're going to get simplification. And then the antiderivative somehow became like that. That looks very different from what we got over there, because obviously Mathematica used an alternative method. But in the end, we get the same answer as before, and of course, the numerical computation is the same as what we got. Well, here's a problem. Back again, because we have to deal with this ds, well, you have to expect rather complicated square root computation where square root can be taken off. But there's an added wrinkle. You have to use integration by part here and integration by substitution there. And did I say this was the easiest problem? Yes, I meant every word of it. Other problems are even more complicated. Well, how about this one? I hope everybody recalls what this one is. This is a cycloid. And okay, shall I show you the animation? No, I didn't include the animation. This is a cycloid, and one arch of a cycloid, and then rotated with respect to the x-axis, and we have something like this, kind of like football shape figure. Okay. And how do we calculate the surface area of this thing? Well, we have to use that surface area formula, excuse me, here it is. So let's copy and paste that thing here. This is what we'll have to do. And then the radius is gonna be just y of t, because we are taking the rotation with respect to the x-axis, and x is 1 plus cosine of t, so that's where you can calculate x prime. Excuse me, I think I made a typo here. X is r times, okay, alright, oh sorry, no, there is no typo there. Okay, there's no typo there. So x is that and y is that. So that y part will be replaced right over here. And then x prime and y prime, you have this kind of computation. And just like we did before, we end up with Pythagorean identity and half angle identity. Consequently, the square root becomes, square root disappears like that. Putting everything in, back in, we are going to end up with this y times that square root. And then after that, what we have this kind of trig integration after foiling it. We're going to have to deal with the antiderivative of this cosine times sine. And let's see, two different angles. You can change it into sum of two trigonometric functions, sine and sine, like this, and consequently we can find out the antiderivative and then the integral. We have something like that. This is one of the rare problems that you can calculate precisely.